Hey guys, it's the LPR Cup here, and we are ready to show you some mathematical tricks which can be useful for the solution of the current episode, which is dedicated to quantum mechanics somehow, and we think that this video would be useful for you. In this video, we will discuss several topics on mathematics, which will help you somehow in terms of using some operations with complex numbers, their definitions, and also some operations, some new information on matrices. So I'd like to remember that there is also a video on matrices in our previous seasons of the LPR Cup, and also, today we are going to discuss what is called Taylor series, which we will use for functions representation. Let's fire away, and we'll start with complex numbers. And let us briefly remind the history of numbers. The first numbers which were used, they were the natural numbers for counting some kind of pieces of something. Yeah, some animals, fruit, vegetables. Then appeared the integers, yeah, so natural and natural with negative sign and also zero. Then people decided to invent fractions, and right fractions are called rational numbers, yeah, and also real numbers, yeah, which include irrational numbers and transcendent numbers also. But what comes next? That is the question, and it was addressed to famous mathematicians of the 18th century. They considered the easiest equation, which might seem to you unsolvable. So x squared plus 1 equals 0, so x squared equals minus 1. That's a bit strange for real numbers, isn't it? Yeah. However, we can write the solution formally. Yeah. So the question is how to interpret this square root of minus 1. And Gauss and other mathematicians decided to invent what is called a complex unit, I. Yeah? And develop this definition, and they invented the whole class of numbers, which is called complex numbers. So they are quite frequently used in physics, as long as they describe different phenomena of waves. They are really useful in quantum mechanics, yeah, and in many other topics. And moreover, they are used for some kind of integrations, and yeah, just a tool for physicians. So we will call a complex number z a plus bi, where z is a complex number, so itself, which is parametrized with two parameters a and b, which belong to real numbers, and they are accordingly called real part and imaginary part of a complex number. So this is the thing which is called algebraic notation of a complex number. As soon as a complex number is parameterized with two parameters, we can draw a plane, which is also called a complex plane, yeah, and describe this complex number in this plane. Real z, imaginary z, and some kind of vector with coordinates a and b. So also we can mark the angle psi, or phi, sorry, yeah, and we can understand that phi is nothing but tangent of b over a. And what we can write also, this vector has the absolute value of z, modulus z, and we can write that z equals modulus cosine phi plus I sine phi, yeah, since sine phi equals b over square root a squared plus b squared, and cosine phi equals a over square root of a squared plus b squared. So the geometry is seen here. So after the algebraic notation, we can also include the geometric notation of a complex number. And moreover, this one is called trigonometric notation. And finally, one more representation which was found by Euler. This is the exponential form or exponential notation. Exponential form of a complex number. So he found that the exponent of degree I phi equals cosine phi plus I sine phi. Well, actually it is a very convenient expression which is widely used in complex analysis, and we will also use it in our further discussion. So now we wrote 4 forms of a complex number, and we can go on. So our complex number z today is a plus bi, complex unit. If you again look at the picture, you can see in it that the absolute value of z squared can be found easily like a squared plus b squared. And if you consider the definition, yeah, that I squared equals -1, you can easily understand that this can be rewritten as a plus bi multiplied by a minus bi. And actually the number, the complex number, which is defined like this, is called the conjugated complex number to z. Conjugated to z. Complex number. Okay, then we can also discuss some definitions of arithmetic operations over complex numbers. So first is adding and subtracting. If we have two numbers, a plus b complex unit and z2 c plus d, then their sum z3 is written in this way. And remember, I said that we operate over complex numbers in such a way that they have two parameters and we use them independently. So the real part of this sum is a plus c, yeah? And this one, the imaginary part of z3 is b plus d. The same works for subtraction. Z2, a minus c plus b minus d. Yeah, so it's real z4, imaginary z4. Multiplication of complex numbers is also as easy as pi. So you can write a plus bi, c plus di, oh sorry, this 5, yeah, z5. And open the brackets, ac plus bc over complex unit, dA over complex unit, and finally b over d, and I by I gives -1, so finally this is a minus sign here. And we can conclude that the real part of z5 is ac minus b over d. Yeah, read z5. And its complex part is dA plus bc. And finally, if we want to find the fraction z1 over z2, we can come up with a trick. We can multiply everything by the conjugated expression to the denominator. Yeah, and here we obtain c squared plus d squared, and here the full expression for ac plus bd minus bci minus dai, yeah? And finally we obtain the result. This is real part of z6 and imaginary part. Yeah. If we want to write the expression with power, so it would be z7, yeah. In the power of n, where n is a natural number, a plus bi in the power of n. We have binom ak, bn minus k, and I in the power of n minus k, where the sum runs from 0 to, to n, yeah, to n. And we stop for a few seconds and discuss that I in the power of 1 is I, complex unit. I in the power of 2 is minus 1. In the power of 3 it's minus I. In the power of 4 it's 1. And so there is a cycle of 4, yeah. Since I in the power of 5 is again I, yeah. If one wants to understand what is the root of z1, yeah, he or she can write the following expression, that it's z, the absolute value of z multiplied by the exponent of I phi, yeah. And since there is the interpretation on the complex plane, each 2 pi degrees, yeah, radians, sorry, we turn into the same point, and we can write then that it's I phi plus 2 pi over k, where now k is an integer number, and let's write it separately, I phi in this way. And if, for instance, would like to, we can understand, by the way, that there is no need to consider all integer numbers, but those starting from 0 and ending with n minus 1, because then the result is going to repeat again and again. And if we like to find the solution for equation. So, what is the solution of this equation and even the geometric representation? Actually, it's quite nice. We draw the complex plane. And draw a circle of radius of 1. So this is the root, the nth root of 1, yeah, it's also 1. So we see the first solution here on the real axis, and then all next solutions are present at angles psi over n, counting from the position of the first found solution. Yeah, so there are many more others. So this is quite nice geometrical representation, and the solution of this equation. And that's all for notation of complex numbers and the arithmetical operations with them. As you see, it's not that hard, and if we look at the parameters as on independent ones and operate with them like with the real numbers, the results are quite applicable, well, in the same way as it was for real numbers. Well, then we continue, and the next part of our today's discussion is matrices. And as you know, some aspects of matrices were discussed earlier in previous seasons of the LPR Cup. And here we will also discuss a few moments on them and how to implement them for the description of some geometry. Well, we can, apart from different operations like summarizing or find the inverted matrix, we can also transpose them. Then, for instance, if we have, well, the simplest example of the quadratic matrix, square matrix, A21, A2n, AN1, AN2, yeah. The transposed matrix is the following one. It saves the main diagonal, yeah, and reflects the elements with the same numbers but in other positions respectively. So here we write A21, here A12, and so what was the string now is written in column. So, oh, sorry, this is 1n, and what was a column becomes a string. So this is the transposed matrix. The interesting thing is how to rewrite such an expression where the matrices are multiplied. You can see that the result won't be A transposed over B transposed. You can do it by writing it with your pencil, but let's have a look on these matrices and try to deduce. So assume that we have two matrices. A and B, and if we take, if we use the multiplication of these matrices, we should use the first row of the first matrix and the first column of the second matrix. And the corresponding elements should be multiplied, and then the results should be added. So we take the first row, the first column, each element we multiplied by the corresponding one and add the result. So this is the result for the first element, A11, B11 plus B21, A12 plus and Bn1, An1. This is the first element of the matrix. Now let's find the second element in a row, and we will call it C. I will write it in red. And in order to obtain C, we understand that we should take the first string and the second column. So the result for C is nothing but A11, B12 plus A12, B12 plus A13, sorry, there should be 2, yeah? B32 plus blah 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 plus 1n Bn2. And if we transpose the multiplication, this C goes there, yeah? It goes there. Yeah, from this position according to the main diagonal. So we should think how to obtain such a result for C by various combinations of A matrix, B matrix, their transposed results, and how to combine them. And I think that it would be quite obvious for you that it's nothing but B transposed over A transposed. Yeah, you see that we have for B transposed, the first string of the B matrix becomes the first column, yeah, and on contrary, the first column becomes the first string, and so the strings and the columns they are interchanging. And we first tried B transposed and multiplied by A transposed, and hence we obtained the desired result. So the correct formula would be AB transposed equals B transposed over A transposed. Well, that's all for matrices themselves. However, we can discuss how matrices can be used for different operators. I would even say linear operators. So, assume that we have a base of vectors. What is actually a base? The simplest example is three-dimensional real space. So we have three base vectors: ax, ex, ey, and ez. Three base vectors, the minimal system of vectors which can be used for the description of any other. So any other vector. So if there is the random vector A, it might be written as alpha over ex plus beta over ey plus gamma over ez, and the coordinates in the corresponding bases, we say the phrase like this is alpha, beta, and gamma. So this is the vector and the space where the operator, which we would call A, would be acting. Acting on what? Acting on vectors. And the product of this action is also a vector. So this is what is done by the operator. It takes the vector, its coordinates in the appropriate basis, and gives the coordinates of the another vector. And if the operator is linear, it means that if we use this operator for the vector xa plus yb, where x and y are real numbers, we obtain the following result, the following vector. So this is the vector again, and this is the vector, and they are scaled by the same time as A and B. It is very interesting, and it gives many fruitful results. As you see, this operator acts on the three-dimensional space and returns the vector in three-dimensional space. So, for the description of such linear operator, we use matrices. So we write matrices, operators, and two arrows. Arrows describing that these terms might be interchangeable. Linear operators, yeah? Precisely said. And also let us briefly remind what the scalar multiplication of vectors is. If we have two vectors A and B with the following coordinates alpha, beta, gamma, psi, phi, he, we obtain the following result. Yeah, scalar multiplication. And if our space where operators can act on vectors has such a thing as scalar multiplications, the definition of length exists, yeah? So it means that we can define the length of vector. It's A over A scalar multiplied, yeah? And there are operators that save the length of vectors. Such operators are called orthogonal ones. Orthogonal operators. Orthogonal operators. It means that they save the length. If we say it more precisely, it saves the scalar product of two vectors. So if we act on vector A and if we act on vector B, their scalar product is the same as the original scalar multiplication of vectors a and b. So those operators with such a property is called orthogonal operators. And as we draw these arrows, there are orthogonal matrices that describe these operators. We give it without a proof via one interesting feature. The transposed matrix multiplied by the itself matrix gives the unity matrix, which is once standing in the main diagonal and 0 in all other places. Yeah, and it might be also shown that the same means that the inverted matrix is nothing but the transposed one for orthogonal operators. What is actually the example of orthogonal operator? Let us have matrix with one parameter phi, and we defined some trigonometry from this phi. So it is given for you to consider what geometrical sense has such a matrix. But we can check that the transposed one is cosine phi, sine phi minus sine phi. And if we take the multiplication of matrices, it means cosine phi, sine phi minus sine phi, and the original matrix. We obtain 1, 0, 0, 1. So originally we know that this matrix is an orthogonal one. We just showed that it has the following property which we discussed, so as some kind of illustration. But what if we consider that our vectors with coordinates alpha, beta, and gamma, with the coordinates which belong to complex numbers? First of all, we should understand that the product of the scalar multiplication should be counted in a bit different way. So if we introduce also vector beta with again psi, phi, and he, which belong to complex numbers. Now the scalar multiplication is described by the following expression: I psi conjugated plus psi conjugated plus beta phi conjugated plus gamma he conjugated. So this is very important that in the spaces with complex numbers there are complex conjugation. We move further and we should find the operators with the same feature, meaning that they save the length of vectors or the scalar product. So now A is called unitary operator. If it saves the scalar product of vectors and it has a little bit different property. So since we have complex conjugation, the matrix which is complex conjugated and transposed both multiplied by the original matrix, it should give again unity matrix. And actually this one is also written as A plus or A cross, yeah, and the procedure itself is called Hermitian conjugation. Yeah, Hermitian conjugation. So A cross A equals unity matrix. And also in the same way, the result for the inverted matrix can be achieved. So again, we should give some kind of the illustration. And again, it is given to you to think over the meaning of the expression which would be written there. It looks like the matrix which I wrote earlier, but a bit changed in order to make it complex. Yeah. If we count A cross, it's cosine phi cosine phi. Then we can transpose. It means that the exponent of I theta sine phi goes there, and minus, sorry, we forgot minus there. So first I write it, and the exponent of I theta sine phi with minus goes there. And then we should not forget to complex conjugate and write here plus and here minus. And then count the result. So if we take the first row and the second column, we obtain what? 1. That's a pleasure for us. Well, the second element in this row is 0. That's great. Then we count this one, and it gives us also 0. And it is seen that the last one is 1. So it's a unity matrix. That's great. And actually, that is all that we wanted to tell you about the unitary operators, which are widely used in the theoretical physics and the physics of fundamental particles, or all terms like the flavor of particles, their spin are described by the unitary operators. And if you are interested, you just should have a deeper insight into it. So the last thing that we should discuss is Taylor series. Serious. I'm not too serious. Yeah. series. So what is the problem stated by Taylor? There are many functions which are called elementary, like sine x, cosine x, 1 plus x in the power of alpha, where alpha belongs to real numbers. But sometimes it is not needed to count the result of this function exactly. And we should find the approximation. And I would even say that we are going to discuss Taylor approximation. Taylor approximation. What is Taylor approximation? It is the polynomial, and it has a finite length. It means that it's not infinite, yeah, so there is something, the expression like ikx in the power of k, starting from 0 to some n, and plus something, yeah, so the error at which we know the result of calculating sine x with this polynomial, yeah. And by the way, Taylor series is the infinite polynomial, so and it gives the exact result for sine, for instance, yeah. So if we calculate this sum from 0 to infinity, it is the exact expression. So first, again, let's give quite ubiquitous, yeah, I would say, illustration, which is read mainly from the other side, I would say. So let us consider the geometrical progression, yeah. So, and the x by which we multiply lies in such an interval. And the result, this sum is infinite. You all know from school calculus that the result is the following, and it might be written as 1 minus x in the power of minus 1. So let us look on it from the other side. If you want to calculate 1 minus x in the power of minus 1, not with the 100% precision, but well, with some good precision, you can write 1 plus x squared and plus until you want to stop it. So this is a Taylor approximation of such a function 1 minus x in the power of minus 1. That's why in many of our problems it is written that you may use the following thing. This is also a Taylor approximation. And note one important thing, that both approximations work in the interval where the absolute value of x is smaller than 1. This is very important from the mathematical point of view. Finally, let us discuss the expression for sine x. So, what is the Taylor approximation for it? Actually, there is a procedure which describes how to obtain all of the needed coefficients for the Taylor polynomial. Yeah, so there is also a term Taylor polynomial. Yeah, and it is given by the following formula: minus 1 in the power of n, x in the power 2n plus 1 divided by 2n plus 1 factorial. So if we calculate it, well, by k, yeah, from 0 to k, plus error of the order of k, yeah, or well, better to say of the order x in the power of k, yeah. So this is the approximation of sine, and you should I would say even should watch at this and this power. So you see that only odd powers are taken here, and it is simply understood because sine x is uneven function, yeah. If we apply sine to minus x, we obtain minus sine x. And we can't say the same for the even powers of x, yeah. So it means that the coefficients for these parts of the polynomial equals 0, yeah, and only uneven ones remain, yeah. So that's it for the mathematical insight. We hope that it would help you to solve the 5th episode of the 4th season of the LPR Cup, and well, we hope, we really do hope that you will find really interesting, since it is dedicated to the sphere of quantum mechanics, and you are given a unique opportunity to touch it while being at school, and this is actually rarely done. So thank you and wish you all the good luck.